So complexity and data structure. So let's talk about complexity just for a minute. So there's these things called, there's this thing called big O notation. So you might have seen things like O of n squared, O of n log n, O of n, and O of 1. So all of these are references to the worst case performance of some kind of an algorithm. So some kind of a program that you're writing. And it's a function that represents what's the worst case. And the n here represents the size of the data that you're dealing with. All right, so O of 1 means that the performance does not depend on the size of the data that you're dealing with. So no matter how big the data is, as long as it fits in your computer's memory, it's going to take the same amount of time to run this. So for instance, if you've got some kind of a data structure where you're storing the length of the items in that data structure, finding the length of that data structure is big O of 1, right? Doesn't matter, you've already stored it, you're just looking it up. Right now, if you had to actually count them, then you'd have to iterate through each item in that data structure. So something where you're not storing the length, and that would be big O of n, right? Because it takes longer to count the items in a bigger data structure than it does in a smaller data structure. And that scales linearly with the number of items. Okay. Oh, and then there's one other one that's in here, which is big O of log n. That fits in between these two. So big O of log n, this would be how long does it take to look up an item in a sorted collection?
Sorry, real quick, what does n, that variable, stand for again?
It's the size of the collection that you're working with, the size of the data, right? So this is how long does it take to look up someone's phone number in a, well, we don't have phone books anymore, but assume that you had a phone book sorted alphabetically. You've got people's names. How long does it take to look up their name in that phone book? It's log of n, because what you do is based on the number, or find the page where the person's name is. So the way that you do this is you look at the center page and you see is their name before or after that center page. And so if it's before it, then you take the left half and you do it again, and you recursively do that. So you see a lot of algorithms that are like that. They sometimes call these divide and conquer algorithms, because you're dividing your problem set and then you're conquering the subdivisions. Okay, the log here is usually referencing base 2. So let's say I had 1,024 pages. Then I have to, I start off with 1024, and I split that. If it's a perfect split, now I have 512 things to search. Now I split that again, 256, goes down to 128, goes down to 64, goes down to 32, to 16, 8, 4, 2, and then I found the item that I'm looking for, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Well, don't count this step. So if you don't count that step, then it's 10 steps, which is equal to, so 10 steps, which is equal to the log base 2 of 1024. So that's why we call it log n. Right? It's typically these divide and conquer type algorithms that are logarithmic. Okay. So O of n just means you're processing each item one time, or you're processing in a constant number of times, right? So that would be if I have an unsorted collection and I want to find a certain item. So I've just got a bunch of name cards and I want to find a certain person's name. Worst case is I've got to look at every single name card before I found their name, right? So that takes me n steps, where n is the number of name cards. Make sense? Okay. So in log n, this is a special one. This is one that we like to see because there's a lot of algorithms that are n squared. So let me talk about n squared algorithms a little bit. So let's say I wanted to sort some numbers. And I'm going to keep, I'm going to sort some index cards. And the approach that I'm going to use to sort these index cards is I'm going to have a sorted stack, which I currently have 0 in, and I've got an unsorted stack, right? So I'm going to pick the first card up and I'm going to put it into the sorted stack in sorted order. Right now, to find the position where it goes in the sorted stack, now when the stack is empty, that's 0 steps. But the bigger my sorted stack is, the longer that takes me, because I'm going to have to go through each item in the sorted stack, right? Assuming that I'm just looking through each item. So that means in order to sort these cards, if I'm looking through each item in the sorted stack, then it'll take me n times log of n, or sorry, it'd be n times n, right? Because the n's, it's kind of the size of the stack. And I've got to do n steps that are each n steps long. So that's an n squared algorithm. Now, if I took advantage of the fact that the sorted cards are sorted and I did a divide and conquer on finding the insertion point, then that would turn this into an n log n, right? So for every card, so for the n, I have a log n problem to solve. So find the insertion point, right? So this is kind of doing things smart. These are generally going to be kind of dumb algorithms, fall into the n squared. All right. So those are the main things that we're interested in from complexity theory and scaling. Any questions about these, first of all? These are like the main classes that we'll look at.
Yeah, can you go back over that example of why the n squared is n squared if you're iterating over the sort?
So let's say instead of so when I actually find the insertion point, I could either find the insertion point by looking through every card in my sorted stack, or I could find the insertion point by using a divide and conquer like I do with a phone book, right? So if I do it by just looking at every card until I find the right place to put it, that's an n squared algorithm, right? Because it becomes big O of n to find that insertion point. So if I did it dumb in that way.
Yeah, so why is that I guess I'm confused about why that. Oh, because you have to go through each item in the unsorted stack and find. Okay, that makes sense.
And it's a little hand wavy. Like a lot of these, I mean, we could probably go through a long proof that shows that it's exactly in, you know, big O of n or whatever. But some of these are hand wavy, and they really have to do with what's the performance of something at the limit. You know, as you scale to very large n's, how does this perform?
Sorry, before you go on, can you explain the log of n one again?
Yeah. So log n is generally going to be some kind of a divide and conquer algorithm. So if I'm being smart about where I'm finding my insertion point, and I've got 1,000 cards, then I can take that 1,000 card problem and turn it into a comparison for the center card, and then it turns into a 512 card problem. And so at each step, I'm cutting the size of the problem in half. And so there are 10 steps until I get down to a problem of size 1.
Okay. And so does it matter what kind of divide and conquer algorithm you're using, or are all of those going to be log of n?
Well, as long as it's dividing the size of the problem by some constant value, it's a log n, right? So if you happen to do something where somehow you're dividing it by log 3 of n, which maybe you've got some way of separating it into a third of the size, then that's still called a log of n. We don't really care about the base because we're being very, well, it turns out that if you change the base, just the way that logarithms work, it's just a constant times the other log. So it doesn't really matter how you do it. But most of these are going to be log of 2 because we're going to split things in half. Typically, that's the way that we do these problems.
For the first time, I actually get the equation now, because log n is just the reverse of exponentiation.
That's right.
Yeah.
Yeah, so x equals log of, I'll make it log base 2 of y, means that 2 to the x equals y.
Yeah.
Those mean the same thing.
That's why it's going backwards or shrinking. Yeah.
Yep. Okay. So, and these again, so obviously if we can do an O1, this is great, right? Because it doesn't matter. We can do it with really large data structures and it's instantaneous, more or less. Now, there's still some hand waving going on here. There are some cases where, because this is dealing with the limits, there's some cases where we might have an n log n algorithm that can be beaten by an n squared algorithm because there's a constant associated with this, right? So maybe each step takes a really long time, right? But we've only got n log n steps, but the steps themselves take too long. Does that make sense? So there is an example of this, and this is kind of a fun little algorithm. You might have learned about FOIL, and I don't even think about FOIL myself, but my wife teaches algebra, so I have to think about it sometimes. That's first, outer, inner, last, and that's when you've got x plus y times z plus w, right? So that's going to be x z is first, plus outer xw, plus inner, which is yz, plus last, which is YW, right? So those are the same thing. That's how you multiply that out. And John's probably thinking of his tutoring where he has to teach people about FOIL.
Very much
so. So FOIL is actually, this is a special case for, we call these binomials because they got two numbers. It's a special case for multiplying two binomials. You can actually extend this, like if you have a trinomial, x plus y plus z times, another trinomial, or even lots and lots of these trinomials. But let's start with just two different, we'll call these multinomials. What you actually have to do is you have to take this part and multiply it by both of these, and sum those, plus this part multiplied by both of these. And so what you actually have is an n squared algorithm, because you have to, so if this is an n multinomial and this is an n multinomial, then we have to have n times n steps to do that, right? There's n times n multiplications here. Does that kind of make sense? Because we got, in this case, it's 2 times 2. So 1, 2, 3, 4 different multiplications you have to do. So this is actually something called convolution. And we actually use this in digital signal processing. It's kind of a weird thing, a weird tie-in for digital signal processing, but you can actually build a digital filter for audio or video or whatever that is based on polynomials, right? So it's basically saying the current sample plus some multiple of the previous sample plus some multiple of the sample before that, and so on, right? So you have like these lags. And so you can do this to like do high pass filters and low pass filters to filter out the high frequencies, the low frequencies, and things like that. So it turns out the input sequence could be represented as a polynomial, and the filter can be represented as a polynomial. And applying the filter to the input sequence gives you the output sequence. The way that you do that is convolution. So it's just multiplying polynomials, big polynomials, right? I don't want to go too much off the deep end here, but there's this thing called the FFT. Have you ever heard of that? Or the discrete, it's a Fourier transform. Okay, so this was something that people discovered, that if they took a signal, and that signal had, it was a digital signal, say 1,024 samples. It turns out that you can convert that from those samples in the, we'll call this the time domain, that can be converted to the frequency domain. So we would take a bunch of signals in the time domain. So 1024 samples here turns into 1024 samples in the frequency domain. So it's a way that you can do math to get all the different frequency components of a signal. And it's the frequencies plus the phase components. But anyway, you start out with 1024 samples, you end up with 1024 samples. So it turns out if you do this FFT, and the FFT is a, well, it's a special case of the DFT, discrete Fourier transform. But the FFT is an big O of n log n steps. Okay, so that algorithm can be done. We won't go into the algorithm, that's way too complicated, and I have to grab my books from college, grad school. So anyway, but it turns out that if you do an FFT and then you do a multiply just of each element of two like x0 times y0, x1 times y1, and each one of the corresponding elements. So FFT multiplication, and then an IFFT, the inverse fast Fourier transform. So it's the same transform, you just do it again. You end up with the same thing that you would have done if you did a convolution. So this is an n log n. This is n steps. This is n log n. Right? So convolution is n squared. And that can actually be transformed using the FFT into a big O of n log n problem, because you just take the biggest part of it as going to be the limit. Right? So it's log n plus, or n log n plus n plus n log n. So it's kind of a cool little trick, if you will, that some people discovered. And so it turns out if you've got really big polynomials and you want to multiply them together, the fastest way to do that is to do an FFT on those two polynomials, then multiply the coefficients from the FFTs, then do an inverse FFT and read the coefficients back off, and that'll be the answer. So anyway, that was kind of mind-blowing to me. I just wanted to kind of throw that in. That's an example of a place where convolution can be used. And so we actually can use this to multiply giant numbers together, because you can think of a giant number as, oh, sorry, go ahead. Or no, that was just an echo. Okay. You can think, well, any number, if you think of it, say 1, 2, 3, 4 is equal to 1 times 10 to the third plus 2 times 10 to the second plus 3 times 10 to the 1 plus 4 times 10 to the 0, which is a polynomial. It's just that x is 10. Right? So if you have really big numbers that you want to multiply together, you can convert them to polynomials, do an FFT and everything, and it ends up being faster, but we're talking like thousands of digits long, at least. Because the FFT itself is kind of slow and it kind of takes a little, it's a big constant factor to pay for. So all of that to say, sometimes there's optimizations that you can make with big O of n type of things, but the constants will make it not feasible, right? So we don't actually, in reality, use FFTs to multiply numbers together when those numbers are like 32 bits or 64 bits or even larger than that. It's when they get to be like thousands of digits long that people start thinking about, well, is there some kind of a weird signal processing thing that we can do to make this run faster? Okay, so we'll just consider that to be an extra, a bonus little thing, that if you need to multiply giant numbers together, then break out your digital signal processing textbooks and you'll find some weirdness there in order to make that even faster. Okay, so let's look at some data structures. Well, I guess one other thing to think about is we've got time versus space. Right, so sometimes we'll say it's big O of n in time, but it's big O of n squared in space, something like that. So maybe sometimes you can trade memory for speed. That's a little bit weird on modern processors because memory costs speed now, because the more memory accesses you do, the slower things get. So if something doesn't fit in cache, then it can make it slow down dramatically, for instance. But sometimes you'll see time-space trade-offs. People talk about performance. All right, so now data structures. So that's your super brief complexity. So data structures.
Hold up. I actually wanted to hear more about the space complexity.
Okay.
I don't know if you could go into that some more.
So it's how much memory do you need in order to implement this algorithm? That's what you would say. So when we get to hash tables, then hash tables use a lot of space in order to get O of 1 performance. So they over-allocate memory compared to something like a list. They use basically they use at least 2 times the memory of a list.
Okay.
DEX use extra memory to get some performance benefits as well.
Okay, so we can talk about that with the data structures then.
Yeah, so
cool.
So the simplest data structure, if I want to store if I want to store multiple items, is an array. Sometimes we'll call this a vector. And in Python, this is implemented as a list. But that happens to be how Python implements the data structure that it calls a list. Most of the time when computer science people are talking about lists, they're talking about linked lists, which is something that Python doesn't have. All right, so I'll focus on the array here. So what an array is it's just a bunch of items in memory, and you can access them by their position. So could be a string or whatever. So if I need to, so I guess space, this is O of n, right? It's based on the size of the list. It's big O of n. So if you wanted to look up, so we'll look at some of the operators in Python. So n, the n operator is going to be big O of n. Because I don't know if there's a G in this list until I've checked every single item. Right, so it scales with the length of the list. Oh, also, this is also tuples. Are using this array data structure. We also have things like append, which does work for lists, but not for tuples. And this is actually, they do this, sorry, not n. It would normally be big O of n. I should just cross this out like this. So we call this a big O of 1 amortized. So there's a trick that they do. Normally, we call this a big O of n to append because you might need to reallocate this and copy A through G before you put in your H. Right? There might not be available memory right here. What I mean with this amortized is there's a specialized data structure that we use, slightly specialized, where we reserve some extra space here. Right? We keep this blank, so there's always room to grow it. And if we ever do need to move it, what we do is we allocate twice the space. So let's say we have a list of 1,000 items, and we have exactly 1,000 items worth of storage space. We need to append the 1,001 item. So when we do that, we actually allocate enough space for 2,000 items. So as you keep appending in the limit, it takes the same amount of time to append, right? Because you keep doubling the amount of space that you're using. So that's kind of cheating to call it amortized, but you don't worry too much about appending onto the end of a list. What about insert? That is going to be big O of n. So if I need to insert something at the beginning of this list, I need to first shift all of these items down by one slot, right? And that is going to be n steps. So every time I append, or every time I insert something at the 0th element, I have to shift everything over. So yeah, big O of n to insert. So that's not great. Delete, or I should say pop. Pop is also a big O of 1, and that's not amortized. Sorry, why did I say n? It's big O of 1. It's not amortized because we're not going to give that space back to the operating system. We'll just keep the extra space around.
I don't quite understand what pop means. Like I understand like the delete and whatever, but the basis for like pop kind of confuses me.
So pop means to remove and return the very last item on the list. So what it does is it gives you G, and then it makes the list be this list right here. So we're basically storing the data, but we're also storing the length. So we made the length go from 7 to 6. So we had to update this number from 7 to 6, and we returned to G, and that's all we had to do on the pop. So that's why that's a big O of 1, because it really doesn't matter how long the list is in order to remove and return that last item, because we're not actually changing the data that's stored on the list, we're just changing the length.
Oh, okay.
Now, if you tried to pop from anywhere else on the list, it would go back to a big O of n, because anything that's beyond the item that you popped, you need to move all the items higher than that down to use up the space. So, and those are these are append is, this only applies when you're appending to the very end of the, well, yeah, appending to the end of the list, that's the case. Insert, at the beginning of the list is what I'm talking about, and pop at the end of the list is what I'm talking about here. Now, there's a specialized thing that sometimes people will talk about called a stack. And whoops. Oh, what did I do? I don't even know what I did. Let's see if I can go back to drawing. Yeah. Yeah, stack. And that is just push and pop. So push means append, and pop means remove and return the last item. And those are nice. And that's the idea is it's supposed to act like a stack of dishes, right? If you've ever, when COVID is over, we can go to buffets again, if you like buffets, and you'll pick up a plate from the stack, right? The problem is that if the buffet is really popular and you get the last plate, there's chances that nobody's used that plate since COVID was active. So who knows? So go right after they've brought out some new plates to put on the stack because they've pushed a bunch of plates on the stack. So we'll call that a first in, it's a last in, first out. Right, so the last state that you push, the last plate that you push on the stack is the first one that you pop back out. So some of those plates on the bottom, they're probably like, Ming Dynasty China type stuff, because that's when they were, that's for a buffet that's been around a long time. Okay, so that's arrays. Other questions about arrays? Okay. I'll also just briefly mention linked lists. So at linked lists,
I have a question. Since lists and I'm wondering about the difference between lists and tuples, if being mutable has any effect on space.
It does.
Python does.
Yeah, lists are going to be a little bit smaller than tuples. I would say they'll be a list will be up to twice as large as a tuple. And I guess one other thing about Python is, although I've been drawing it as though these items were actually in the list, the way that Python's actually implementing this is it doesn't actually store the items right there. What it does is it stores what's called a pointer or a memory address of the item. And so those items themselves that are in the list are stored elsewhere. So we call this the heap. So you might think when you're assigning variables in Python, you're just moving references, or you're making a reference to an object. So those objects all kind of live on this heap thing. And so the list itself is just a list of pointers or a list of references, which means that it is possible to append a list onto itself, and you end up with something that looks like this, which is kind of a weird thing to do, but it's certainly possible. So you can have a list that's contained within itself. Really weird. Not something that I found a lot of use for, but is kind of a cool thing to do. Okay. Other questions about arrays, Python lists? Actually, let me mention one other specialized data structure here, and that is the deck. So a deck has a special append left and pop left. So a deck is a specialized list. And both of these are going to be big O of 1 in time. Okay. So it does some special logic, basically, to allow you to work with the left-hand side of the collection as well as the right-hand side. And so it pays for it in memory. So it uses some extra bookkeeping, and I'm not as familiar with exactly the way that Python implements the deck. But if you need something where you can push and pop onto either end just as fast, you might want to look at a deck.
I have a question going back to the list. Sorry, I was having technical issues. So if you wanted to, let's say, increase, I'm just thinking also, I saw a recent example of a NumPy or NumPy array. And if you had a list of numbers and you wanted to increase the value of all the numbers by 1,
Mhm.
would that, you can iterate over every item in the list, and I'm guessing that would be O of n.
Yes.
But what would be the time complexity, I guess, if you're able to, I'm not sure if you can do the list, I can't remember, but just increase all the values at once by some value.
Right. So it's still going to be big O of n to do that, because you still have to do that many multiplications or additions or whatever you're doing. The reason why we use NumPy is there's this constant that's associated with all of these scaling algorithms, right? So it takes, I don't tell you how many microseconds it takes to do a big an n operation. So actually, let's say we're adding an element to, or adding or multiplying every element in this Python list by a certain value. Well, that might take a millisecond. Probably not a millisecond. It'll take a few tens of nanoseconds at least to do those multiplications for each one of the multiplications, because it's got to load the item from memory, find it on the heap, multiply the value, write the value back out, things like that. What NumPy does is it takes that constant and it makes it really, really small. Because it's implemented in C, it doesn't actually use the same storage. It's actually going to store the numbers directly there, so there's no extra memory lookup. And it's going to use all the processor specialized instructions that you might have on your CPU, where it can do things like multiply 4 numbers times 4 numbers, because sometimes we'll call these the streaming SIMD extensions or SIMD instructions. So a lot of processors do have the ability to load 4 numbers from memory at the same time, multiply those 4 numbers by another 4 numbers, and then store them all back. And so you get a big speed up by doing that. But it's still, the scaling is still going to be big O of n, because it still ultimately has to do the same work.
Okay. But that's confusing me, I guess, a little bit. Like if you're iterating over every single one, that's also going to be big O of n. But what I was reading or whatever is just that one's going to be much more efficient than the other in terms of simultaneously doing them all at the same time.
Well,
just
from a scalability standpoint, big O of n is the same thing as big O of n divided by 4. Right? Constants go away.
Okay.
So this would be a NumPy, or we'll call this a SIMD. And we'll call this, I don't know, so it might take a quarter of the number of steps, but as your problem doubles in size, then it takes twice as long. That's really what we're looking at. As the array doubles in size, what happens to your runtime? Does it double? If the runtime doubles when your input size doubles, then it's big O of n. Right? Now, if it was, the reason why we use NumPy is because both the original and the doubled runtime is a lot better than it would be if we did it with regular pure Python. Right? Okay, so that's lists and DEX being a special case of list Q. So the K, or the QUE here, that's just the actual queue. This is a first in, first out data structure, which means that you can push onto one end and you can pop off of the other. And or sometimes we'll call this put and get, or we'll call it append left and pop. Now it's a double-ended queue because you can also make it go the other direction, right? You're also allowed to do an append and a pop left, because it turns out if you can do the data structure that lets you do these efficiently, also lets you go the other direction. So, and then one free pun is the definition of Q is a letter Q followed by 4 letters silently waiting their turn. So there you go, your free pun. Okay, so that's those are some other data structures and or yeah, some more, these are all array-like, right? They're still going to be storing things in the same way, or at least similar. Queues do a little bit of extra stuff, but they have a lot of the same. And in all of these cases, finding something by its position is big O of 1, right? Because we just need to take, basically it's the starting index, or the starting memory location of this data structure, the position, and then the number of bytes that each position takes up. So it's just a single multiplication to find where you need to look for this item. So,
related to my other question, so because the time complexity is really kind of looking at a scalability perspective, how, like, what's the, I don't know, domain or like terminology, or how do you figure out kind of what is the most efficient implementation for a specific case, I guess? Like, how would you know to use, or a NumPy array versus a standard Python list, I guess?
So if you don't need to resize it, so NumPy arrays are not great at resizing. That's one thing that I just happen to know. If you're not going to be resizing and you're dealing with numerical data, NumPy is always going to be a lot faster.
But like, is there any kind of like, I don't know, notation other than just like experience and knowing the data structures in depth for kind of figuring out that?
I mean, if you've got NumPy available, then it's almost always going to be the better way to do it. That's what I would say about that. It's just a really efficient implementation of numerical algorithms for Python. The built-in data structures have a lot of flexibility, right? If you've got something that's not entirely numerical, maybe it's mixed numerical and string content, or if it's a bunch of strings or something like that, then the Python data structure may be better. Or at least you don't give up anything by using Python, right? NumPy will be equally inefficient because it's still going to be storing things in this way. And there's really not a lot of array type operations that you do on a list of strings, right? And then Pandas does a lot of that. Pandas will give you support for lists of strings, but it's doing it through Python, right? So Pandas is just storing, that's why it calls it an object column. Just like, I'm not going to use NumPy for this. I'm just going to call it an object, so it's a Python object, right? Okay. So the next one that I want to talk about is, and let me do this. I'm going to skip forward to the hash table. Oops. And in Python, this is a dict or a set. So the neat thing about these is in is big O of 1. So constant time to look up an item. So the reason that this works is, say you've got some key. So I want to say look up some value corresponding to some key, right? So the way that I do this is I've got something called a hash function, which is just it's some math function that I apply on the key. So I'll call this the hval. So I get some number out of this, and this is always going to be a number, right? I then say my index is going to be the hval mod the table size. All right, so my hash file might be a really big number, but this is going to convert it to a number between 0 and the table size. And what that's telling me is, if this key exists in my hash table, then it will be located at this index. Okay? So the hash table itself is a really sparse data structure. So it mostly will be nulls. And occasionally it will have some value in here for like the thing that we're looking for, key. And that points to whatever the value was. All right, so this hashing function is all the magic there. So hashing, the Python hash function, when it hashes small integers, it gives you the same small integer back, because those are kind of guaranteed not to conflict. The big danger of a hash table is what happens if two different keys hash to the same value, or more particularly, what happens if the index that gets generated here is the same index. If that happens, we have what's called a hash collision. So when that hash collision happens, there's different ways that you can deal with that. You could turn this into a linked list. So in this case, we would store a small data structure here that actually allows you to have multiple values in the same slot. Maybe I should call this a slot number. I don't think that's what Python does. I think what Python does is it just goes up to the next hash value and it tries to store it there. But the more collisions you have, the slower this gets. And so there was actually an attack. It was a denial of service attack that people figured out that if you provided certain keys in your web requests, then it would cause all sorts of massive hash collisions when people tried to take the keys that you provided on the URL string and put it into a dictionary or some kind of a hash table. And so you end up with this hash table, which is huge because it's trying to allocate enough space to store this data, but they're all collisions, right? Because they were crafted to all collide because someone knew what this hash function was. So people now randomize these a little bit. So they use a little bit of a cryptographic flavor so that your hash tables are not always so easy to predict what that where the slots are going to be stored, so you don't get as many collisions. Anyway, the collisions are what is bad. So if your collision, like let's say you somehow collided everything, this big O of 1 becomes a big O of n with collisions. But what we do is we make sure that there's enough space so that we very infrequently have collisions in the hash table. So this is the perfect example of size versus or time-space trade-offs, space-time trade-offs, right? I'm trying to make it sound like Einstein here. So the more space you have, the less likely there is to be a collision, and the closer you're going to approach big O of 1. So whenever you have something that's a non-trivial size, like more than 2 or 3, then a dictionary or a set will probably be faster than a list for computing in or looking something up by its key.
Is it slower to create that dictionary?
Well, it allocates a little bit
than,
more
say,
memory.
a list?
Yeah, so allocating the memory will take a little bit longer, but not that much. I mean, you could do little micro benchmarks with time it in a Jupyter notebook, but it's not going to be. I don't worry too much about the creation time. It's the, if you've got a lot of these that you're storing, if you're dealing with a large number of hash tables or a large number of dictionaries, that can start to take up some space, or start to take up a large amount of space, which can slow things down because it's using so much memory. Your cache isn't very good. So if you don't know what the key value pairs are, then hash tables are really good. If you do know what the key value pairs are, you might look at a named tuple. Named tuple is a tuple where we just give each one of those positions a name. So the neat thing about a named tuple is we don't actually need to use up all this space. We're just storing tuples, and then based on the type of the tuple, we just know that, oh, well, you said a.foo, you really mean the third offset of a. And so it does that translation. And so that's a quick translation going from name to position, and then it is able to get the rest of it. And I guess technically the number of names, you're still going to have an index between, name goes to position, but usually you just have this for a handful of positions. So this is going to be pretty small lookup. Okay, so the lists, list tuples and list tuples, dictionaries, and sets are what we use most of the time in Python, right? So if you need things by position, then you can very quickly find them by their position using a list or a tuple. But if you need to find them based on some key value, then a dictionary is going to be better. Now, dictionary or hash tables themselves don't give you a way to deal with positions very cleanly, right? So you can iterate over a hash table, iterate over a Python dictionary, you'll get the keys. Python gives you those keys in the order in which you inserted the keys into the dictionary. And that's, but you can't change that order, right? So the order is kind of fixed based on how you created the dictionary, how it got those keys into it. Generally speaking, in older versions of Python before 3.6, you didn't even get that guaranteed. In fact, if you kept adding items to a dictionary, the key order could change, right? Because as a dictionary grows, let's say it does get to a certain size where it might start getting collisions, what it's going to do is it's going to, again, double the space that's allocated, and it's going to rehash all the values, right? It does that infrequently, so we kind of can ignore it. But that rehashing could have changed the order in which the keys showed up. Now, Python 3.6 and above guarantee that that doesn't happen. It's going to give you the same key order. But as far as complexity goes, this is big O of 1 in most cases. It does use up more memory, and it does not give you the ability to deal with things by their position.
Sorry, this is kind of a basic question, but can you remind me what a set is? I've forgotten that.
Yeah, a set is, it's kind of like a list, except that you're not allowed to have duplicates inside it. So I put this in with dictionaries because it's implemented the same way. And before we had sets, we used dictionaries for them because the dictionary keys are a set, right? You can't have two keys with the same value in a dictionary. Okay, so what we did before we had sets is that we just had dictionaries where all the values were none. So sets have a few other methods which let you do things like set union and set difference and set intersection and set exclusive or and things like that. But sets do not guarantee the order to be the same as you inserted it, which is weird because it's implemented by the same underlying data structure. I guess they haven't gotten around to that optimization, or maybe they thought it would be confusing.
Is the syntax for sets curly braces as well, but just separated with commas?
Yes.
Okay.
Sets are curly braces, no colons, and dictionaries are curly braces with colons. And if you want an empty set, you have to say set, because curly brace is, that's an empty dictionary, because dictionaries are older than sets in Python. So, okay. Kind of mentioned one other data structure. I'll just mention it again, the linked list. These are basically things that look like this. You've got data, and you've got a next. So this is a simple linked list right here. Whoops, what did I do? I don't know what that button does. Okay. Next. So these are just pointers. And you've got some data that you care about, and then a pointer that you don't, or that, you know, the pointer is basically just, you know, where is it? What is the next element on the list? There's different implementations of this. There's doubly linked lists where you've got a next and a previous. There's circular linked lists where they make the, where basically the last element goes and links into the first element. Yeah, those are, sometimes you'll have sentinel values. So they'll have a special item on the end, which means end of list item. They'll have a special item on the beginning, which means beginning of list item. Those are all implementation details. Python doesn't really do these because this is going to be O of n to look up an item. It's going to be O of n, it's going to be O of n to look up an item by position. Position or value. The only benefit that this has is if you've already got a pointer to your item, then inserting an item into the list at a known, you know, after an item that you already have a pointer to is an O of 1. Sorry, O of 1. I'll call this insert after. So if you already know where you are and you need to put an item in, then you can splice it in. You could also call this a splice. So some people will say, well, that, you know, if you're going to be inserting at arbitrary positions, then you should definitely use a linked list. That's not actually true. Vectors are going to be faster than that. One reason is finding the position of insertion is an O of n operation here, right? You still have to iterate through this to find where you need to put it. And in fact, if you go back to the name cards example, if you have name cards stored as a linked list, you're going to have to go the O of n to find your insertion point. You can't do it with a big O of log n, right? Because even though it's sorted, you still don't know what the middle element is. You don't know how to get there. So anyway, I had a friend who was like, you know, people will say, well, inserting into a linked list is faster. He was like, well, I'm not sure that it really is. And so what he did is he basically just had something that always inserted at the beginning. Actually, I think it was always at the beginning. Anyway, he wanted to compare a linked list versus a vector. Turns out the vector was still faster because vectors use the cache much more effectively on your CPU. What the cache will do is it takes data from your main memory, which is relatively slow, and it puts it in really fast memory. Vectors tend to, and what it does is when it does bring something in from slow memory to fast memory, it brings the surrounding data as well, not just the particular item that you're looking at, but it assumes that you might be accessing nearby data as well in the near future. And so let's go ahead and grab a whole, we call it a cache line. When it does that, if you go back to the arrays, well, sorry, go back to arrays here. Since the arrays are stored like this, they're contiguous. If you do a cache miss and you fetch this item, then you probably are going to bring back a whole bunch of items, right? That's not the case necessarily with a linked list. In a linked list, if you do a miss on this item could be somewhere else entirely. It's not guaranteed to be contiguous in memory, and so you probably do cache miss, cache miss, cache miss, and it ends up slowing things down. So even though theoretically it might be faster with a linked list, practically most of the time it's going to be slower because your CPU cache is so much faster. Okay, so linked lists are there. We don't use them too much. There's other things like there's binary trees.
Is there a different measurement for that? Sorry. So if big O notation is for the theoretic, like worst case, is there a notation for the practical measurement?
Well, I don't know that there's one for the scalability. There probably
terminology
is. There probably is one, but it's really it's a constant factor issue. So like even if you had something that was theoretically faster here, it might be that the constant was so large that linked lists are still not going to be great. Like it's still, so big O of 1, remember, is big O of 2 to the 99th, right? But I certainly don't want an algorithm that has this performance because that's a really big number. Because 2 to the 99th is a constant and 1 is a constant. So in big O notation, they mean the same thing.
And that can also change, I guess, depending on the machine, right? Because
yeah, so if you go back to some really old machines that don't have cache, then linked lists will probably outperform vectors in a lot of cases. Right? You never have to reallocate everything in a linked list, right? Inserting something never requires you to shift things, and that's great. But it turns out shifting things is really fast if you've got a cache. So that's where the benefit is coming. Okay, so linked lists are a thing. There's also things that you'll sometimes see called binary trees. And so this is where we've got some, let's say I've got some values. Like this. And so what you're storing in this case is you've got a value as well as a left and a right pointer. And we don't have anything that's built into Python that does this. So that would be a balanced binary tree. So that's just a nice way of being able to have something that you can quickly add things to it. So adding something to a binary tree is big O of log n. right? Because you just have to find your path to the bottom is going to be log of n if this is balanced, right? It's going to be the log of n of the total number of items. So in this case, we've got 7 items. So it's 1, 2, well, 3 basically, up to 3 steps. And then you decide whether it goes onto the left or the right-hand side. So if I want to put in 5.5, say is 5.5 less than or greater than 4? It's greater than this. Is it less than or greater than 6? It's less than that, and it's less than or greater than 5, so it's greater than that. So this is where my 5.5 would go, right? So 3 comparisons that I've got to make. And that's because this was, that was 2 to the 8th minus 1 items in it. So balanced binary trees, that's insert, delete, basically all of your operations in, find, those are all going to be log of n because you're always tracing a path from the root of the tree. And then there are ways that you can modify this tree to keep it relatively balanced. So there's algorithms that would let you keep that up to date as you go. We don't do this too much. There's a specialization of this, which is used a lot with databases, which is called a B tree. And so instead of having a binary tree, it's a block tree. And so what it does is it doesn't have just 2 children. It'll have multiple children based on whatever your storage system is. And so there's different pivot points. Basically, it'll have, it'll say, well, anything that is between these two, inside this range will be stored in this child. Anything that's in this range will be stored in this child, and so on. Right? So it breaks up your space into larger numbers. So it basically makes a really short and fat tree, and it sizes these. So when we had rotating disks, then it sized these to be the size of a disk block. So retrieving any node of this B tree was really fast. So when you'll find things like indexes are implemented as B trees. So in MongoDB, I don't know if it's still the case, but it used to be the case that all of their indexes were B trees. And so if you needed to, say, iterate through something, well, let's say you had a timestamp, and you're always adding things onto your, you're adding new events as they come up. So turns out what would happen in that case is you always had the largest portion of your index in memory, right? As it tried to find out what index do I need to update? It was always something along this rightmost area because it was always the largest timestamps that were in the database. Now, if you started doing random lookups in this, then it would have to bring all these other things into memory, which could slow things down. But that was a trick that we would use in order to use the indexes efficiently and use our memory efficiently, is just make sure that you are only accessing things at either the right or the left of the index. Right? So it still is able to handle other things, but it's most efficient when it only has the single path to deal with. Okay. And then I guess one other thing is the heap. So a heap is a neat one. What a heap is it's a balanced tree, a balanced binary tree. It's not actually stored this way. Since it's always perfectly balanced, they actually just store it as an array. And the guarantee of the heap is that every item, I should say value of some node, is going to be less than the value of the child of n. Okay, so I can have a 1 here. Actually, let me just put these out to the side. A 1 here, a 10, and a 3 here. And I could have a, 11 and 42. I could have 75 and 6. This is a valid heap, right? It's not sorted. It's not a sorted binary tree, but I can easily find the smallest value. That's O of 1, right? Always going to be the root. turns out I can also, if I do any modifications, so add or remove, those are going to be O of log n. So if I wanted to add something here, what I'd actually do is I would put it at the end of the tree. Actually, I think the end of the tree in this case would be here. And if I, let's say I had a 7, I wanted to put in here. It says, well, you have violated this, so I'm going to have to swap these. So it'll look at this and, this has got nothing in it. So nothing is there. So it'll actually swap these values. And then I get a 7 and an 11 down here. And then it looks at these. It says, oh, you violated this again. So it has to swap it again. So now the 7 is up here. And this becomes a 10. Wait. Yeah. And now this has now been rectified, right? So my insertion worked. Removing the smallest, and I should say, maybe I should call this not remove, but pop. That's also going to be a log of n, because what you do is you just take this one off and you grab the last one and you put it there, and then you do the same little propagation back down into the tree. So those are log of n. This is great for priority queues. This is where we want to insert things in any order, but we always want to get the highest priority thing off at first. So so the heap queue module in Python is used for priority queues, or it's used for this heap type operation. Now, heap queue does not have a data structure. It uses lists as its underlying data structure, because it turns out that it makes more sense if you do this with a one-based type thing. If you just number these, then root the level 1 children, which should be at 7. So to find your kids basically in this tree, you simply I think you just multiply you round your, well, you just multiply yourself by 2. Yeah, you multiply yourself by 2. So it's your index times 2 or your index times 2 plus 1. Those are your 2 kids. So that's the way that this is stored. And so there's a little bit of extra work that goes on if you do these zero-based like Python does, but roughly that's how it's working. And so that's why I said it looks like logically it's a binary tree. Physically, it's stored as an array. All right. So there is one, and I'll end with this unless there's questions. So heaps, we can add arbitrary elements to them with O of log n. We can remove items from them, or we can remove the smallest O of log n, right? So what if I wanted to sort numbers, right? So I could say for in sequence, and then I can say while so that is n steps to do a login operation. So that's n log n. This is also going to be n steps because I'm going to pop off all the items while I still have items on the heap. This is also a log n. So that is a 2 times O of n, or sorry, yeah, n log n, which is basically an n log n operation. So this is
what about sorting the list?
Well, I'm saying, oh, in this case, we're yielding them off in sorted order.
But initially, we needed to sort the list.
Nope, it was unsorted. The sequence is unsorted.
Oh, I thought the first step there was sort.
Oh no, this is this is how I'm implementing sorts.
Oh, I see. Okay.
And we call this heap sort.
I see. Okay.
We don't actually have to do heap sort. Like the built-in sort in Python is faster. It has all sorts of crazy optimizations that they do for real world optimizations, because it turns out most data is not sorted randomly. Most data is somewhat sorted, right? You'll have runs of things that are sorted. And so there's the special implementation that they use in Python is called TimSort. It's after Tim Peters, who came up with all these special heuristics and optimizations. And so TimSort is one of the fastest sorting algorithms out there. And I guess, so I found this one really, really fun. And then one, I said I would end there, but when we sort things, and we can sorted things, we typically say there's some sequence, and you have a key, which is optional, you know. So what that key is it's, you know, it's some function to call on each one of the items in the sequence to get the sort key, whatever you're sorting by. So we used to be able to do this with sort, a sequence, and a comparison. And that comparison was something that you would run. So it would be basically comparison with A and B would be -1 if A is less than B, 0 if A is equal to B, and 1, or positive if A is greater than B. So you can do this with subtraction, right? So that was great for numbers. You could do it with subtraction. Turns out this is really slow if you do this in Python, because sorting, any kind of sorting with a binary comparison, is in log n. And there's proofs for why that's true, as to why this is the best you'll ever do with sorting algorithms, is in log n. Problem is, so it's in log n comparisons. And if your comparison function is written in Python, then it's a slow function. If you're comparing native types, like if you're comparing integers, this is fast. Python function. This is slow, right? So we don't do this anymore in preference for something like this. Because what we do with this sorted is we'll actually call the key function for the item in sequence, right? So that is big O of n, right? You're calling the function for at once for every item. So it's big O of n calls to the Python function. And then it's doing a bunch of less than operations, but it's going to do n log n of those. So let's assume that this key function is slow. Well, it's slow, but it's scaling really well, right? It's scaling better than n log n. The really fast operation is the one that we do more times, and the really slow operation is the thing that we only do a smaller number of times. And so that's why sorting, you know, doing this key function is much better than providing a comparison function there, right? Because it's going to call the comparison function n log n times, it's going to call the key function n times.
Right. So the comparison function is what's happening in the material table custom sort components that we can add.
Okay.
It returns a true false based on some comparison that you give it. So is that fast in JavaScript?
Well, it's still going to scale the same way.
Okay.
So it's still going to do it in log n steps. Probably you're not dealing with a large enough n to make it make a big difference.
Yeah.
Right. If you're dealing with 10 or 20, it's not going to be that big of a deal. But if you got a much larger thing to sort, then it could take some time.